I should discuss? Oh, the audience will discuss. Right. Could you speak up a little bit? Just to shout. It depends how far out your refined regions go. Just the domain regions go.
Sure.
I just don't remember how far they go in those simulations.
It's substantially above.
Huh?
Yeah, it's substantially larger than a virial radius, but it's not, 100 megaparsecs.
Wow.
That's embedded doors.
Yeah, so you get the right potential of large scales anywhere, right? Low resolution regions. I don't know why the high resolution regions matter.
But the potential probably get right. The question is whether you get the right distribution of satellites. How many satellites you're missing because you're not resolving them.
Right. But
if we go to megaparsec, that's fine.
Yeah.
That answers my question.
You're resolving the Lagrangian region.
Yeah. I mean, the Lagrangian region is resolved because we can see the number of.
No, it's matter that it's Lagrangian region with video radius, with 3 video radius, with 5 video radius. That actually matters. But if it's like 5 video radius, yeah, that's more than enough. Okay. Are we done with discussion? Running out of steam? You get coffee, guys, so you're not allowed to speak. Neil, you don't want to say?
Actually, I'm curious about one thing for the runs. I mean, there's been a lot of discussion and about whether or not stellar feedback can modify the dark matter profiles of payloads. It didn't seem like either extreme. I mean, it's possible there's some sweet spot in the middle. In the ones we just saw, that there was much change in the dark matter profile.
Well, we have more of that all these factors we can become further models which are quite clear progress, but it gives a some level so we will work further.
Actually, Sebastian showed a plot that did seem to show modification, and he said it seemed to be consistent with the basically governmental result, right?
So we didn't really complain with it, because it's some effects.
No, but he showed the dark matter profile.
So it's a bit like.
And it seemed quite significantly
So
black
compared to the
within 1 kiloparsec was
So you were
flattened.
okay. Sorry, I misread the plot.
The rotation curve looked about the same.
But it still requires social experiment. Because in that warp galaxy, what is the storm mass? It says 8 plus storm mass.
Yeah, 1.4%.
And I'm thinking the oscillations in order to do the flattening, you need to have more than 10% which means that if you go with warps, like warp toroidals, you don't have that. There's some issue how you do the flattening if you want it.
I don't think you need to do any flattening for those steroids. For those steroids, you don't need to do any flattening.
Well, there are these measurements.
Huh?
So the question is, what about format? So there are two pretty convincing sets of measurements that do suggest that Fornax does have a flattening core.
See, other results we don't need that.
Pardon?
I see NASA results which say that we don't do that.
I don't think
No,
it's,
I'm talking about observation.
yeah, what
We don't
observations
see
are.
observations of
So this is the Penn-Rubia observations, and their point is that they found that the higher metallicity stars and the lower metallicity stars, which are easy to distinguish spectroscopically, seem to be at two different radii. And so that allowed them, I mean, this is a published paper, and it looks really pretty good. I've discussed it with experts who seem to agree with it. It's hard to see how you get around this. So because they're able to separate these two different radii, they can actually see what the potential is of those two different radii, and it appears that Fornax, the most massive of the dwarfs, does have a core.
It's not just Fornax, it's also Sculptor, where they actually
The
have
argument
stronger.
for Sculptor seems to be weaker, but
Well,
yeah,
they
possibly also
claim it's a
Sculptor.
stronger result.
All right. Anyway, yes, the claim is also true for Sculptor.
So in both
I
cases where they
personally, I
found these
actually was
multiple
more impressed with
populations.
the data on Fornax.
Well, but in both cases where they found multiple populations, they argued
Right.
uniqueness. So.
Exactly. So I mean, you know, this is real data. It's hard to see how it could be really wrong. So I don't know what other data you're talking about, but this is a recent paper, and there was that other independent measurement by this other group, I forget, which got similar results.
The
Anyway.
Schwarzschild model.
No, that I regarded as being much less impressive. Because
I mean,
you
how,
get-
you have to make some assumptions, right, Joe, about making assumptions that about orbits of those populations, because otherwise you can
No,
take,
that's not true.
No.
That's not true.
I can take all the stars, there's numbers, and they take even and odd numbers. How different it is from,
It's not true.
you know, how different it is just taking every other star, saying it's one population.
But the thing is that Fornax and the Simpson Sculptor do have a lot of stars. Fornax also has 5 popular clusters. I mean, the point is that it may be quite massive enough so that the calculations by Rook and Governado et al. Actually do apply and would explain the flattening. The real problem, I mean,
Well, I mean, Joel, can I comment on that?
Sure.
One point that Jorge has made in a follow-up paper that Mike is more familiar with than I am, because I've basically read the abstract, is that, you know, the argument is to actually make cores is much harder than it is to just lower the densities.
yes.
So the point is that that's an even, there's sort of 2 levels of the problem. You just want to lower the density, or you want to really make a full-on core. And the making of the core appears to be harder than just lowering the density.
What I'm referring to is the paper by Governado et al. Called
I know, that's-
Testing No More. And in that paper, they're actually showing that around the mass of Fornax, they can get cores.
Well, they,
So you have to be careful with testing those plots.
It's an isolated dwarf galaxy, and so it has a rich star formation history down to redshift of 0.
I see.
So you can continue to have this core formation process taking place at all
Okay, well,
redshifts.
that's not the star
That's
formation
your
history that we
satellite.
see for Fornax. So,
Right, if you're a satellite and you fall in it, for example, Z has to cut off. And so you end up not forming as strong of a core, but just having reduced dark matter density.
thanks very much for that clarification. I don't remember that statement being in the
Well, it wasn't in
Testing No More paper.
You will see it, it's in Solitop 2012. when I was
Okay, well,
showing it.
very good.
That
So
paper was
Solomon
about-
was talking right now, so explain this to it.
Right, it's important to clarify too that that paper was about field dwarfs and
Yes.
things, and you know the core size and the flatness of the dwarfs around the Milky Way is arguably flatter
Yep,
than,
okay, good
than
point.
this sort of marginal core.
Of course, doing such simulations with full resolution is much more difficult if you want to have a big galaxy in it. So you have to treat the big galaxy as basically some kind of static thing, or you couldn't do a full simulation with the big galaxy and the dwarf simultaneously.
Okay, well, let's finish on this optimistic note, because we only have slightly more than an hour for lunch, and presumably we'll be talking during lunch about the evening.
In the simulations, at least, it's the radial orbits of the dark matters, allowing you to preferentially strip dark matter from the core.
Yes. I mean, yeah, I think it would be a bad sign if we saw stellar streams from these things, because once you can actually get down to start stripping stars, you should destroy this thing almost instantaneously at that point.
I wanted to raise a question that I think Allison addressed, sort of, but it's one of the things that was kind of emphasized in the 2012 version of the Boylan-Colchin et al., and that is, yes, and that is the complete failure of abundance matching below a certain scale. So what we found is that abundance matching, many people have found this, Risa Wexler et al., Sebastian Trujillo Gomez et al. Paper, our second Bolshoi paper, that abundance matching seems to work extremely well, down to 80 kilometers a second halos or something like that. But what you guys emphasized, Boylan-Colchin et al. 2012, was that it fails miserably for the things galaxies, and especially as you go down to the lower masses of the Milky Way dwarfs. And to some extent, your too big to fail problem is kind of the extreme example of that. What you emphasized was that the Draco dwarf, which is one of the smaller dwarfs, actually seems to be sitting in the highest circular velocity halo. And Fornax, which is the most massive in terms of its stellar mass, is not sitting in a very high mass halo. So, question, can you shed any more light, especially Allison, because you did address this, on where we can expect abundance matching to work and where it fails and why it fails?
I guess it depends on what you mean by failure, right? Because if you're talking these field galaxies, things galaxies, I mean, that is, Governado 2012, right? So that is where you expect to see core creation happening. That's like a sweet spot. And so you are reducing what you would find for dark matter masses in these galaxies compared to what you get out of a dark matter only simulation. So, in that case, it's not the gigantic scatter plot, but it will significantly deviate from just doing a simulation dark matter only matching to the stellar mass function of SDSS. That it will deviate from that because of it.
I'm not sure that we're talking about the same thing. It fails when baryonic Thalia-Fisher relation fails. Because how you do the matching, right?
But what if
where does that
where does that fail?
Oh, that fails to 10 kilometers per second. I mean, it goes all the way down to 10 kilometers per second.
Yeah, but abundance matching fails at something like 50 or...
It depends what you mention. That's the whole point. If you mention mass, then you fail. But if instead of we mention central velocity dispersion or at a 1 kiloparsec, whatever the fraction you're observing, that actually doesn't.
Well, so the things that you can try to match are either luminosity, stellar luminosity, or total baryonic mass. Whole baryons plus stars.
Yes,
those
but it's baryonic Thalia-Fisher relation, which is known to go very much down. It's a quantity which you're using. If you're using the mass of a halo in matching with luminosity, then it fails miserably. But if instead of using the central part of dark matter of the galaxy, then it's still doing okay.
But it's not with abundance matching because already, well, as you showed in the work with Ferrachense, or in the comparison with either the HiPACC or alfalfa, you start to get a serious deviation at like 80 kilometers a second. So yes, I mean, if you assume that those baryons are all visible and have the circular velocity...
No, they're not. I mean, their luminosity is much smaller, right? This is what it is. You say velocity is right, but luminosity is not. Anyway, that's slightly...
Or that you're not picking up the circular velocity of the halo.
Because you don't see it turn over.
Hydrogen isn't being detected far enough out. Anyway, I mean, I think that that's one of the crucial questions. It doesn't really mean that cold dark matter has failed, but it means that trying to understand these dwarfy galaxies
I've got a plot to
gets
show you.
harder.
I've got a plot to show you after this.
So I guess I'd just like to make like a comment for discussion at some level. I definitely agree that baryons matter, right? I mean, we have to include them. But one of the reasons why, bringing in people from other fields, I think one of the reasons why people from outside our field don't necessarily take us seriously is we're a field of postdictions, right? The problem pops up, modelers go crazy, they can reproduce it, right? But what we need to do is think about predictions. Like, how can we test the scenario? And one of the nice things about what you guys are saying, I think, is that, at least as it stands right now, low stellar mass systems in the field that have not been affected by tides ought to look denser. than their counterparts. And so they're, or maybe not. I mean, I don't know, but I mean, maybe that's a start at least. I mean, and there are low mass galaxies in the field with mass measurements that look low. I mean, I don't. It's
James, I have like 24 of them, very high quality. I don't know what to do with them. Interpretation extremely complicated. Because you have a very large line width, like a 2H alpha, the line width is 25 kilometers per second. Rotational velocity is flat and 10 kilometers per second. What you do? If you add asymmetric drift correction, you get 10 times bigger mass. If you don't, it has 10 times smaller.
Well, just in the local group, there's galaxies like Cetus that have velocity dispersions that have mass within 300 parsecs of 10 to 7 solar masses, for example. That looks a lot like a local group dwarf. I mean, a Milky Way dwarf. I don't know how many of, I mean, I think it'd be worth it for us to push out beyond the real radius anyway, because there will always be concerns about tides.
Well, and I think also, given that there's a lot more parameter space in terms of discovery, given, I mean, there's the SDSS coverage, but there's all kinds of stuff coming online now in the south, and presumably more will be discovered. It's another good motivation for making predictions for this, both in terms of numbers and area coverage, things like that.
Yeah, so this is a question for Allison, actually. So you mentioned that many of the satellites which came in got destroyed. And I was wondering
I'd be cautious to say many. Some do, yeah.
I was just wondering if your predictions for the halo stars were consistent with the very low fraction of halo stars in the Milky Way.
Oh, I think so. I guess Dee would be the expert on this. She's looked at the stellar halo formation in these particular simulations.
So the ones that have been destroyed, presumably have lost all their stars.
Okay, so unlike the young people of this panel, I am one of the people who represent some historical perspective on this topic here. So I'd like to make some, with your permission, some personal comments on my views on this. To me, and to many of my colleagues, it was pretty obvious 30 years ago that baryons matter and make a big difference to the dark halo structure, even before we knew about cold dark matter. Remember, before we knew about halos, long before we knew about cold dark. So Galois feedback was an obvious thing to do something, and we showed that it's doing a lot. I was therefore very surprised when I heard James and Mike making such strong statement about the problem, how they call it, too hard to fail. And I heard a report on our friend Carlos Frank speaking on the BBC radio or TV, saying that he no longer sleeps at night because of the small-scale problems of CDM. This was a few months ago. So I was surprised, but also happy, because it's nice that these things come up again, and this makes them very sexy to deal with, because people don't sleep at night. And so the idea that supernova feedback can erase cusps and make cores and lower density and all this, and so on. James Bullock wrote a paper on this when he was a postdoc. Gnedin and Zhao, it's you, right? Or your brother?
No, it's another one.
No, it's the other one.
So the other candidate in Zao wrote a nice paper.
They didn't find an effect though from baryons, so be careful. They did not find an effect from
Well,
baryons.
you have to read papers.
Oh, okay, okay.
They just have a very simple simulation and show that if you remove stuff quickly, the cast becomes a core.
Which is wrong statement.
Now let me make my comment on. I think that we are still, even though we've done a lot of progress, the way we deal with star formation and feedback, and I think Alison alluded to this, in our simulation, any simulation, is still premature, a lot of ad hoc assumptions. The governmental prescription is very nice, it's giving nice results, but it's an ad hoc prescription. And so are all the others. And any of us who've done this knows how difficult it is and how ad hoc our assumptions are. So I personally am not very impressed by the simulation results, except that they give us feasibility tests. They show us that baryons may solve the problem. What I'm more impressed by is those simplified toy analytic estimates, like the one of Ponzanetine. You know, we all remember the adiabatic contraction, things that Joel came up with Blumenthal and Flores and so on. Very simple argument about why we should expect adiabatic contraction. The same thing is true about impulsive getting rid of matter, impulsive expansion. If you do the calculation, you find that impulsive expansion is more effective than adiabatic contraction. And if you just have several bursts of this kind, you will puff up your system. I'm much more impressed by this simplified argument, giving us hope that in the day when we will have a simulation where we believe the feedback recipe and the star formation, we will have the right solution. And I'd be extremely surprised if this wouldn't work.
Well, an interesting counterpoint to that, I don't know the history as well, but in the old simulations, you used to always see adiabatic contraction. Now as time's gone on, there's less and less contraction.
Yeah, that's true.
I wonder if there's a parallel here.
Overexpansion?
I understand your point, Abishai. I mean, at some level too, I think we want to be careful we're not just fooling ourselves. I mean, we obviously know the answer we want to get. We want to match the data. And are we getting ourselves into a trap that we're just rerunning and retuning and creating and cooking up models that can give us the observations that are clearly there, as opposed to sort of taking a sober look at what the situation is and seeing like maybe nature is trying to tell us something.
No, but I would reverse it and say we should in parallel. This is like the same analytic game, right? We do it with simulations, but we have the feedback is the same analytic. In parallel, we should study the theory of feedback and try to do it right. And we are not there yet, is what I'm saying. We miss basic physical theory of how feedback works, all kinds of feedback, and then how to implement it in the simulations. And we should do it independently, without even knowing what the data is, right? But we are not there yet, so we're playing the game in the two parallel ways.
Phil, you were next. Do you want to say something?
Well, largely what I was going to say, I've already been sort of getting this discussion. I would say in response to that, I mean, very much agree with what Abishai is saying about needing to explore feedback more fully. And on those notes, I would say, I think maybe it's not giving the rest of the community enough credit to say that we don't understand feedback at all. I think there's a lot that's been worked on in other communities that we don't, having our blinders on and just talking about, cosmology and galaxy formation on a large scale that we're ignoring, that a lot of people put a lot of hard work into. And there's a lot to probably be gained without reinventing the wheel by looking at work.
Joel and David?
I think Avishai's point was to state it very simply that you should never trust a simulation until you understand it more or less analytically. And I think we all need to keep that in mind, because simulations can't be treated as black boxes. But I wanted to ask a completely different question that I think we have to come back to. It's a question that James emphasized years ago, and that Rachel Cusio de Nere has very effectively reminded us about, and I think it's her latest paper. And that's the low surface brightness galaxies. These are extremely common galaxies. they often have circular velocities of well over 100 kilometers a second. These are not little dwarfy systems. And yet, they have so low stellar surface densities that it's hard to see how they could drive these repeated episodes of gas removal and baryon and dark matter expansion that appear to be necessary to understand their fairly low surface densities, fairly low central densities of dark matter. So, especially addressed to the many, well, okay, so that's the question I was going to ask, is, but are you really reproducing the systematics of the dwarf spheroidal, sorry, of the low surface brightness galaxies?
They have central surface brightnesses less than 23 magnitudes per square second, and they have...
So which paper is this? Certainly it's not the Caspian Omar paper, and it's... Okay, but you haven't published a paper on this yet that I'm aware of.
No, but it's...
Okay, so why, so now, okay, so... Maybe you can clarify what your current status is, because as far as I know, that's still a major unsolved problem.
Okay, so, well, I mean, I'm just going to say the basics of what I know here, right? I mean, you're talking about things that kind of lie in the sweet spot, actually, of where core formation seems to be the most effective, because they have a deep enough potential well to have these extended star formation histories with repeated bursts. Right, you don't need much, right? And when they do go off, they blow out tons of gas. It changes the potential, and then later on, you know, you can go on and form some more stars. So they lie in the stellar mass to halo mass relationship. So something is going on, right? Where you can get the proper amount of star formation and end up with these LSBs.
In the spirit of what James is saying, that we have to make predictions.
Sure.
Is there some way that we can test that this is the scenario that really explains them? Namely, repeated episodes of blowout. How can we tell if that's true?
I have some thoughts on that. Namely, in terms of the process that creates cores also reshuffles the stars. And so you can use the age and chemical gradients to actually say something about the past history of these galaxies.
Have you ever seen physical examples of this blowout phenomenon? Have we seen it in galaxies like that at earlier redshifts?
At earlier, can we ask an observer that one? Yeah.
Or to put it differently, what would be the predictions that you make as to what people ought to see?
In fact, I was going to suggest that maybe observations might be helpful among the observers like ourselves. We've been seeing all kinds of creatures over the years. I mean, we have a whole class of objects called blue compact dwarfs, for example. If you calculate how much energy is in the star formation activity, it's hundreds of times the potential energy that we see because velocity dispersions are small. I'm not talking about low surface. That's not my point. All I'm saying is that there are different kinds of galaxies out there for which observations have been collected, which may serve as extreme examples that may serve as tests of some of these scenarios. For example, I see bumps and wiggles up there of the star formation when there are blowouts, etc. Well, if we're doing a systematic set of surveys and you tell us, gee, if you can go down to 10 to the 8, David, let's say a redshift of 0.1 or 0.2, which is easy for us, we can cover enough area, and you say, we should find a duty cycle time, pick a number, 20%. Well, then, okay, we'll look at 20% of the things that are some stellar mass, and you're telling us that we should see blowouts, I mean, some sort of winds, say, when I can give you those numbers, not right now, but you can be a driver for our observations and surveys by making these predictions, which James is suggesting. This is an example. Or these blue dwarfs. Well, we have numbers of them. We have number density. We have volume density. We can tell you how much energy they are. They are, in terms of mass loading function, mass loading factors, they're huge in some cases. And so if you don't ever produce those, well, they exist. So that means you have to do something to your models to explain them as well as others. So I think there's a room here for some more interaction between the theorists and the observers. And I'm very excited by some of these things because you're... Pardon? Yeah, we have extremes of those kinds. And there's also tests, for example, recycled gas has metallicity implications. We can measure those quite well, for example. And so there's certain type of measurements that are amenable for, I think, comparison at phases which you are predicting, but we don't see them in the resultant fossil products of these dwarfs that we see, or just around our Milky Way.